Interstellar objects, ISOs, in short, are astronomical objects passing through our solar system on an unbounded hyperbolic trajectory about the Sun. They represent one of the last unexplored classes of solar system objects, which could sample planetesimals and primitive materials of the ancient past. Such interstellar travelers, not gravitationally bound to any star, may have witnessed the various secrets of our vast and mysterious universe we are yet to unravel. The first known ISO, called Oumuamua, which means messenger in Hawaiian, was discovered on October 19, 2017, by the University of Hawaii's Pan-STARRS telescope. This unexpected visitor from interstellar space had been wandering through the Milky Way for hundreds of millions of years. 2 years later, on August 29, 2019, a Crimean amateur astronomer and telescope maker, Gennady Borisov, found the second interstellar object, dubbed Borisov after his name, entering our solar system after its long and lonely interstellar journey. It is estimated to be about 0.61 miles in size, traveling at a blistering speed of about 110,000 miles per hour, when observed later by the Hubble Space Telescope. Also, according to the United States Space Command, a small meteorite measuring just 1.5 feet across, blazed through the skies and crashed into the ocean just off the coast of Papua New Guinea, on January 8, 2014, was actually the third ISO impacted Earth, 3 years before the identification of Oumuamua. ISOs are physical laboratories that would enable studying interstellar space in situ, rather than remotely using telescopes such as the Hubble or James Webb. These yellow curves are some fictitious ISO trajectories, simulated using a recent study on the ISO number density and population, which could be considered as possible targets for future exploration. They are indeed hyperbolic about the Sun, passing through our solar system having a high inclination and high velocity as in the cases of Oumuamua and Borisov. Due to these characteristics, exploring ISOs with conventional human-in-the-loop guidance and control techniques is significantly difficult. The purpose of this study is to develop a first-ever deep learning-based framework to encounter any fast-moving objects, including such interstellar visitors wandering through the universe unattached to any star system, robustly, accurately, and autonomously in real time. The GNC, guidance, navigation, and control of this mission, can be split into two segments: the cruise phase, and the terminal phase. During the cruise phase, the spacecraft uses state estimation obtained by ground-based telescopes, and navigates via ground-in-the-loop operations. Unfortunately, conventional GNC frameworks could fail, due to the poorly constrained orbits of the ISOs during this phase. The typical ISO state uncertainty, which is much larger than that of the conventional exploration targets, even at the end of the cruise phase, is depicted by the yellow balls. Let us take a closer look at this picture, in a spacecraft relative frame centered on the ISO. This illustrates the second phase of the GNC, the terminal phase, where the spacecraft switches to fully autonomous operation. The proposed approach, called neural rendezvous, is like a spacecraft's intelligent brain, which determines optimal actions to take based on the current estimated states of the ISO and spacecraft. The Caltech and NASA JPL researchers show that the actions computed by neural rendezvous are indeed near optimal in realizing the close encounter with the ISO. Furthermore, the distance from the ISO at the encounter is mathematically guaranteed to be small. The blue ball centered on the ISO indicates the bound of this distance. In numerical simulations, it is demonstrated that neural rendezvous outperforms other existing guidance and control algorithms. These white dots are the spacecraft terminal positions, when the spacecraft naively uses a pre-computed desired trajectory, with an existing non-linear feedback control policy, constructed using the knowledge of Lagrangian systems. You can see that the spacecraft sometimes achieves the encounter, but in most cases, it just fails to do it. Similarly, the red dots represent the spacecraft terminal positions for the case of the proportional derivative control, or PD control, with the same pre-computed trajectory, where the variance of the delivery errors is still too large for its practical use. These observations indicate that it is critical to update the desired trajectory along the way, in order to achieve a small delivery error at the encounter with the ISO. The next approach is based on Model Predictive Control, MPC in short, reformulated to be computed in real time using the linearized dynamics of the spacecraft. Since it exploits the MPC to update its desired trajectory, this technique consistently achieves smaller delivery errors, possessing a smaller delivery error variance when compared with the previous two techniques. However, most of their errors are still larger than the probabilistic delivery error bound of neural rendezvous, indicated by the blue ball. The next yellow dots are the terminal positions of the spacecraft, equipped with the learning-based guidance, which approximates the MPC by the spectrally normalized neural network. Since it is shown to have a finite optimality gap with respect to nonlinear MPC, this approach results in a better delivery error performance. The proposed approach, neural rendezvous, probabilistically guarantees that the delivery error at the ISO encounter is smaller than the error bound. You can see that the simulated delivery errors are indeed smaller than the bound in a probabilistic sense, as expected. Having such a verifiable mathematical guarantee, even with the use of machine learning, is indispensable to designing control and autonomy engines for safety-critical robotic missions on land, in water, or in deep space, and hence the major strength of neural rendezvous. Let us go back to the original movie, showing the fictitious ISO trajectories for possible future exploration. We can indeed see that neural rendezvous achieves small delivery error for all of these ISO candidates, robustly, accurately, and autonomously in real time, even under the large ISO state uncertainty and high-velocity challenges. Such verifiable and real-time optimality, stability, and robustness guarantees will provide invaluable analytical insight into evaluating the performance of such machine learning techniques, thereby substantially enhancing conventional black box AI-based guidance and control approaches. Neural rendezvous and its guarantees are general enough to be used not only for encountering ISOs, but also for solving various nonlinear autonomous rendezvous problems with fast-moving objects, accurately in real time under external disturbances, and various sources of uncertainty. The Caltech and NASA JPL team has been working on validating its performance on an actual spacecraft. And the initial test run worked beautifully as expected, where the spacecraft trajectory is indicated by the light trail. Please follow the links in our description to learn more about this study, and stay tuned for exciting simulation results coming soon.